So welcome everybody. Oh, there we go. Now we're live. Welcome everybody. This is Philip Weinberg. I am hosting today's seminar, and today we have the Northeastern Quantum Matter Seminar, that is. And today we have Joel Moore as our seminar speaker, and he'll be giving us a seminar on electron hydrodynamics and low dimensional metals. So with that, Joel, please go ahead and take it away.
Thank you, and hello to everyone out there in Zoom space. I am not very experienced at this kind of seminar, and I realize that there's a diversity of backgrounds on the call, so I will do my best. I think we're going to take questions at the end, but I hope there will be plenty of questions at any level, and I can go back to slides that are relevant then. There are really a couple of parts to this talk, but they're all about what I'll think of as hydrodynamical behavior in metals that is different from a conventional fluid like water or something like that. And let me start by defining a few concepts, and then we'll go through one case in one dimension where we can make very precise statements, and then we can test them numerically. And then the last part of the talk is about higher dimensions where there are more experiments, but there are fewer controlled ways to know that what you're talking about is real. So my picture of what hydrodynamics is, well, we believe that the underlying description of the universe is quantum mechanical. And we believe that most systems thermalize to some kind of Gibbs ensemble, even if they are closed quantum systems, as long as they're chaotic and complicated enough. We know that there are exceptions to that general rule. It could be that you just don't thermalize. You have something like many-body localization is one well-known physical way that you could fail to reach equilibrium. One possibility is that you do reach equilibrium of some form, but equilibrium is modified, or that the process by which you evolve toward equilibrium, which is what we usually think of as hydrodynamics, that process is modified compared to an ordinary fluid or something like that. So I want to start with a nice example where a lot of work has been done by a lot of people, especially in the last 4 or 5 years, which is that we now understand a different kind of hydrodynamics that exists in some one-dimensional systems related to integrability. And I'll define that, but basically it means having a lot of conservation laws beyond the ones that we're used to, like energy. And then part 2 is about, well, in the real world, we probably are not exactly integrable, even if we have one-dimensional wires. And we kind of know that maybe systems are not that stable once we break integrability. It turns out that there are at least some cases where interesting things still happen in realistic one-dimensional systems. And then I'll talk a little bit about what are some active questions in higher dimensions. So maybe this is a bit like a colloquium in that there are a couple of different topics, but they're all tied together. They're all unusual things, unusual ways that I'd say the electron fluid in a metal without disorder is different from what we're used to when we think about a fluid, or what we're used to when we think about a metal with impurities and our sort of standard Boltzmann transport. So what I think of as the standard picture of computing transport in solids is about linear response theory. And that idea you can understand classically, and like many good things in physics, it really goes back to Einstein, whose point was that if you want to understand linear response coefficients like the diffusion coefficient in Fick's law, this number d, those are actually related. So that's a question about, if I move a little bit away from equilibrium, how do I get back to equilibrium? That's actually related to an equilibrium dynamical correlation function. So if you just watch the Brownian particle move around, this heavy particle in a fluid of light particles, you'll find that it jiggles. Brown thought the particle was alive, but that turns out not always to be true. Even if it's not alive, it still jiggles around. And if you watch its velocity autocorrelation function, you can actually get the diffusion constant. So that's the basic idea of linear response theory, fluctuation, dissipation, ideas like that. Of course, we use that in solids all the time. That's where our formulas for electrical conductivity in metals come from. So here's a little bit more on how this actually works in solids usually. So we'd like to calculate, for example, electrical conductivity, which is some expression very similar in spirit, even though it's notationally more complicated, to what I just showed you about the diffusion constant. This is the electrical conductivity on the left, and on the right is some current correlation function. So for this to be finite, we need the current eventually to relax in time. This is an integral over time. So the idea is that in order to get a finite conductivity, there has to be some memory only for a finite time in the current. After a while, it gets back to equilibrium wherever it started. And we know that that is not always the case, and this talk includes some of the exceptions to that general rule. And then we can do various perturbative approaches to try to calculate the Kubo formula. But I'm mostly going to be interested in cases where the electrical conductivity does not behave in ways that we would expect, either in terms of its not existing or in terms of its variation with temperature or something like that. But this is sort of the standard model that we're looking for exceptions to. So in 1D, I'm going to go more or less in historical order to talk about one of the amazing things that's special in 1D, and it's very pretty. It has been applied to a few experiments, but not very many. But there's an enormous number of theory papers, and it was really rejuvenated by some work starting in 2016. But before that, I'm going to talk about a simpler example that is easy and exact and serves as a check on the more general methods. And the classic problem that sort of stimulated a lot of the recent work is something called the true reservoir quench. If you want to test whether your system has normal transport response or something unusual, and if you want to drive it far from equilibrium, this is a way that can be done either experimentally or numerically. It's easy to see what it does in free cases, and it's now understood what it does in a wide variety of integrable models, but that was only quite recent progress. So what I will do is start off with a special case, that's kind of point one. And then it turns out that there is now a very general version of hydrodynamics for integrable models. And this is the work that I said, I mean, there were hints before, but I'd say it really got going around 2016. Basically, for many quantum one-dimensional problems that we all know and love, like the Hubbard model or the one-dimensional Heisenberg spin chain or something like that, we now understand how to start with essentially an arbitrary initial condition that will rapidly reach local equilibrium. So for example, you'll have some local notion of energy density and things like that. And then over time, that will evolve, but how that evolves and how it's different from a normal fluid, that's what we can write equations for, sometimes called either generalized hydrodynamics or Bethe-Boltzmann equation or whatever. You can view it as either hydrodynamics or kinetic theory, whichever you find more intuitive. And then I'll start getting back to the physical world. So standard hydrodynamics is the question of getting from local equilibrium to global equilibrium. And what I mean by local equilibrium is that we assume that things like the average temperature and the average pressure are well defined. And in air, for example, that happens in a fraction of a microsecond. But then there are very slow processes taking seconds or minutes or days for the fluid to stream around and reach global equilibrium. And that's what equations like this are useful for. And these are the simplest possible hydrodynamic equations. They don't have things like viscosity. You need to go to first order to get those. I'll say a tiny bit about viscosity at the end, because that's one of the things that people are now measuring for electron gases. But for now, this is standard hydro. Now, one question you might ask, why are there only 3 equations here? And the answer is that in a usual fluid, there are 3 conserved quantities. The first one, the continuity equation, comes from conservation of particle number. When 2 particles collide, there are still 2 particles that come out. The second one is about conservation of momentum, and the third one is about conservation of energy. So what's special in 1D is that there are very many systems where there are more than just those 3 conserved quantities. They're actually an infinite list, but for the first problem I'm going to solve, I only need 1 more conserved quantity, and that gives us a simple example of how hydrodynamics might be modified in useful ways, and I'm mostly going to use it as a check for what's going on. So the examples I'm going to talk about are basically the one-dimensional Bose gas with delta function interaction, which is relevant to a lot of atomic experiments. And then what's more relevant to solids, and what I'm going to say more about, is the so-called XXZ spin chain, which is this version of a spin-half model on a one-dimensional chain where I've allowed the interactions to be anisotropic. There might be a different Z interaction from X and Y. And I also might talk about magnetic fields at various points. So both of these have been solvable for their thermodynamics going back to the 1960s. Although it turns out that there was an enormous amount that was missed about the XXZ spin chain. Basically, half of the conservation laws were not well understood until work of Prozin around 2011. But now we think we understand the thermodynamics well. And it turns out that the point of this hydrodynamical approach to these one-dimensional models is going to be that you can get a lot out of the thermodynamic stuff that people already knew, but I'll come to that. So when I say there are an infinite number of conserved quantities, I just want to show you what they are. And this is the last time I'm going to write down one of these infinite lists, because as you can see, they get very complicated. So this is just the XXZ spin chain. And there is another reason why I have this. So the point is, unlike just having energy and momentum, there's actually some infinite list where the code here is that sigma z xxz actually means 4 spin operators on neighboring sites. There's an infinite list of conserved currents, and then also an infinite list of conserved charges. And the one thing which is a little bit special, which is the first thing we're going to use about the XXZ model, is that there's a special point in these infinite lists. Oops. Sorry, I seem to have lost my window. Not sure what I did. There. In these infinite lists, there is one conserved quantity, which is conserved as a density, but it's also the current of something else. Basically, the energy current is itself a conserved charge, which is a little unusual, but we can use it to make some checks. So here's the 2 reservoir quench that we're going to use as our test problem. It's just take an infinite one-dimensional line, heat up the left side, say to a different temperature than the right side, and then let it go. And this is nowadays not too hard to do with DMRG type simulations. And let me first just solve this very quickly for free particles and explain how they don't quite reach equilibrium because they're free. They just pass right through each other. And then we can ask our integrable models, which have interactions. As you might guess, they're somewhere in between the free models and the fully thermalizing interacting models. But this is the problem. When I show numerics, it will often be about this, that I've got some one-dimensional integrable model on the full line, but I've prepared an initial condition that is inhomogeneous, which is normally the way fluids work, if you think about it. The Hamiltonian is uniform in space, but we've prepared an initial state that is not uniform, and then we watch it move around. So the simplest picture, if I've got a free model, it's actually related to the Stefan-Boltzmann law of total energy transport that you learned a long time ago, like the radiation from a black body. So if I take a one-dimensional free system, then you could imagine hot particles coming from the left lead in both directions and cold particles coming from the right lead in both directions. And if I look at the region between the 2 leads, then it's not in equilibrium because the right movers are at a different temperature than the left movers. And there's some current that will survive at this position for long times. So you can do the same thing for free bosons at any temperature with any dispersion. And one thing that you get that's kind of nice, if you ask what is the energy conductivity from calculating this initial setup, you get this equation at the bottom, which is the so-called thermal conductance quantum. This is exactly the same calculation that you might have seen for energy transport, for charge transport, that the conductance of a wire is E squared over H times the number of channels. Now it's this thing, which involves temperature and Boltzmann's constant as well. And an interesting thing is that unlike for charge conductance, the thermal conductance quantum is actually universal between bosons and fermions. It's just related to the central charge of the CFT. Okay, so that's the free case. Now let's do something a little bit harder. And the technical way to ask this question about do things just move through each other without relaxing is called, is there a Drude weight? Which means if I look at a conductivity as a function of frequency, is it finite as omega goes to 0, or does it have a diverging peak? So one example that people know about when you hear Drude weight is a superconductor. There you've got some diverging transport by the condensate. And another example, which kind of generalizes what happens with free particles, is that if I remember what the Kubo formula definition of this conductivity is, it's some average in time of a current correlation function. To be precise, the conductivity is the integral, and then this d will be non-zero if the limit doesn't fall off, if j of t doesn't fall off as it goes to infinity. And one way that can happen is if the current is protected because it's proportional to a conserved quantity. These q sub k's are the conserved quantities of a system. So for example, if current is proportional to momentum and momentum is conserved, then if you start particles going, they will just keep on going forever. And that's an easy way to get a diverging conductivity. So the little story about spin transport, which through Jordan Wegener is equivalent to transport of a one-dimensional interacting fermion in this XXZ model, is that even though people knew the thermodynamics of this model a long time ago, by 1970 or so, they did not know the right conserved quantities that would prove that this Drude weight is actually non-zero. So it was only understood starting around 2011 that there is ballistic transport of spin in this class of models. And that's kind of a lead-in to try to quantify how does transport work. So I would say, maybe 2016 was when hydrodynamical approaches got going, but this work around 2011 was very important in suggesting that a lot of what we knew about thermodynamics in these models was, first of all, incomplete. But if you added to it, if you knew the full thermodynamics, like these extra conserved quantities, that would help you understand things like whether or not there's a Drude weight, which is kind of the most basic dynamical question, whether the conductivity is infinite or finite. So I want to talk about two quantities in one-dimensional systems. One is, if I prepare this two-reservoir quench, the natural electronics experiment would be how much current is there across the boundary. When you do it with atoms, it's more natural to do something like a quantum gas microscope, which you might have heard about recently in this seminar series, and ask, can I take a picture of how densities are moving and then try to quantify that picture maybe in terms of moments or the density. And it turns out that the second one of these is surprisingly easy to calculate for integrable models like XXZ. And it's maybe a first example of this incorporating extra quantities into hydrodynamics. And I'm going to go through it quickly and then present the general theory, because in hindsight, the general theory is really not any more work if you're willing to believe me on a couple of points than the special theory. But this is what I mean by quantifying an expansion. It just means I started with a step function in energy density because I prepared my system that way, and I let it go and it spreads out. And I could ask, how much did the first moment of the energy distribution, say, increase in time because of the particles moving around? So that is a reasonable quantity to try to compute. And here's how you get it exactly for the XXZ model. Well, first, these are some numerical experiments you can do. I'll come back to those. So what's going on is that there's an extra hydrodynamical equation, if you like, beyond the standard ones. And that's this fact that the energy current, which appears in the continuity equation for energy, so this is the equivalent of the third equation in standard hydrodynamics, has its own extra equation. This is the fourth equation that is not there in standard hydrodynamics, which is that the energy current has a very special property. It's also a conserved charge. It's both a charge and a current. And using that, you can crank through some algebra and get sort of simple exact predictions where you can take thermodynamics of the XXZ model and ask for any initial temperature gradient, no matter how much temperature difference between the left and the right there is, how rapidly does the energy expand? How does that first moment change in time? And you can compare that to numerics, and it works. So this is one special case using one extra hydrodynamical equation for one specific problem. But at least this is a sign that it's not crazy, because the bottom line, for those of you who work in the field, if I turn off the Z interaction between spins, then it's actually a simple free fermion model. So everyone believes we could calculate that analytically. And then you can use this extra hydrodynamical equation to get the Heisenberg model. So this is saying that even for a very far from equilibrium quench in the Heisenberg model, you can get some exact results about how energy moves around. And we did that around 2015. So now, here's the relatively recent progress, although now I think we can say a lot of things are understood. And then I'll jump into more physical cases that are less exactly solvable. But basically, two groups in 2016 found exact solutions for this initial condition, not just for this question about the moments, but for the full spreading, essentially. And it turns out that those can be generalized even to other profiles. And it turns out that this approach, which I'm going to sketch for you, because I think it's a very beautiful and intuitive picture, it's actually been known to work for some time for classical integrable models, like the gas of solitons and the nonlinear Schrodinger equation. So the basic idea is going to be, you can take what you know about statics and thermodynamics and convert that to a kind of equation for quasi-particles. And the equation that you get is very similar between quantum integral models and classical integral models, which is maybe not that unusual in hydrodynamical problems. If you have enough particles and you wait long enough and you ask the right question, sometimes the emergent behavior is classical. And that seems to be the case here. So we can sketch the picture and then test it. And here's the one equation that's going to kind of capture everything. And it is possible to give a full talk on this integrable model business. There are many full talks. You could probably even find one online. I just want to sketch why it works and show that it works, and derivations and things like that. I will refer you to other sources. But here's the basic idea. If I took a Boltzmann equation, normally there's an increase in entropy and a thermalization because there are collisions between the particles on the right-hand side. Here, there are no collisions. So this is just like a streaming equation. Things move around. However, there's one difference, which is the way that the velocity term is written. Normally, you would have v partial x rho. That would be the streaming term or convective term in the Boltzmann equation. Here, the interesting fact is that the velocity of one particle at momentum k at some space-time point depends on the velocity of all the other particles. Sorry, depends on how many other particles there are at other momenta at the same space-time point. And that idea basically comes back to what's special about solvable models and the Bethe ansatz. It's basically that when particles pass through each other, they either delay each other or shift each other's phase, depending on your classical or quantum worldview. But they do that in kind of an additive way. There are no new 3 or 4 particle interactions. They kind of factorize into 2 particle interactions. So to kind of show a picture of that, the way that integral models work, and here for students in the audience, maybe this is a worthwhile takeaway. If I were to take solitons in like optical fiber in the nonlinear Schrödinger equation, what I would find, the neat thing about these integrable equations is that the solitons affect each other, but they retain their integrity and they keep propagating, and they propagate out to infinity, but they've delayed each other during the region where they were interacting. So this is space and time. And 2 classical solitons interacting with each other retain their integrity, but delay each other. Quantum mechanically, there's a phase shift, but a phase shift is semi-classically related to a time delay if the phase shift is energy dependent. So that's what makes the hydrodynamics of integral models special. And I really would think of it as a kinetic theory of either solitons or particles. They don't collide and randomize their momenta. They keep their momenta, but they delay each other. And if you can keep track of those delays, which is just the effective velocity in this Boltzmann equation, then you're done. So the magic is in that v function, the velocity form, and that is a fairly technical calculation in some cases from the Bethe ansatz, but that's been done classically. It's now been done in a number of quantum models. The one that we use most heavily is the calculation for XXE, which is a PRL by these 4 people. So in a sense, this is a surprise. It's different from what we're used to, even though I made it sound straightforward, because usually I think of kinetic theory like the Boltzmann equation as a fundamentally different description from Euler equations like hydrodynamics. And yet here I'm claiming that they're sort of the same thing. In fact, they're similar enough that people disagree maybe about what to call this kind of theory. I don't think it matters too much. I guess the way to understand why kinetic theory of particles is the same thing as fluid equations here is the following. The way they're different in classical systems is that the Boltzmann equation is for the full 1 particle distribution. And hydrodynamics is only for 3 numbers about that distribution: the total number of particles, the total momentum density, and the total energy density. But if we're talking about an integrable system, and here the simplest case to write down these quantities is basically the Bose gas with delta function repulsion, this Lieb-Liniger model, then there's an infinite list of conserved quantities, which means it wouldn't be right to just think about the first 3. That would be ordinary hydrodynamics. We should think about all of them, which is basically all moments of the particle distribution function. But basically, under some assumptions like positivity and falling off at infinity, if you have all the moments of the function, that is the same information as the function. So this is saying that kinetic theory is really the same thing as working with an infinite number of conservation laws. And the kinetic theory is just one equation in these models, so you might as well work with that. And what's kind of deep is that this equivalence between what we normally think of as conservation laws and kinetic theory it works even for models where the conservation laws are much more complicated, like XXZ. That's kind of the technical comment down at the bottom of the slide. All right, so to kind of test this, if you want, the picture is the following. A normal fluid goes from an initial state to local equilibrium, then through hydrodynamics to global equilibrium. This is saying that integrable fluids, many of our favorite models in 1 dimensions, they go to a different sort of local equilibrium, which has many conservation laws. That's usually called generalized Gibbs equilibrium. And then through either this infinite list of hydrodynamical equations or this one Boltzmann-like equation that evolves in time. And that was solved for 2 reservoirs, the full scaling function, not just the one number that was already known around 2016. So let's just try out this approach for general solutions in X and T, where we may not have an analytic check, but we can compare to DMRG. And here's an example, and I'll zoom in on one of these in case they're hard to see. But the point of this is that every one of these plots is a time-dependent DMRG calculation in gold overlaid on the predictions of the hydrodynamical theory in blue. And all of these calculations are about the XXZ model, so an interacting spin model. You know, it's a quantum system of very many particles, the kind of thing that we usually think of as not easy. And I've prepared some initial state of energy density at t equal to 0, and then let it evolve in time. So the right-hand side is basically the 2 reservoir quench, that kind of test problem I talked about before. But even if you just take one lump and watch it split, so you've got some complicated curves in time, it does seem like hydrodynamics is exact for the long time limits of these integrable models, that it's capturing the most important physics, which is just a statement that these curves seem controllably close on top of each other. If you do the calculation more accurately, they sit more and more closely on top of each other. So the corrections are related to if the temperature is very low, it takes time to get into local equilibrium. And if the density is very low, then you would expect variation. And there's a lot of work now on understanding those corrections. But basically, this is a kind of hydrodynamics that seems to work very well. And again, zooming in more, I don't know whether this is more a check on time-dependent DMRG or more a check on hydrodynamical equations, but these are 2 very different sets of equations that seem to predict the same behavior. So that gives us some confidence that for the integral models, where we have all these special facts, like these infinitely many conservation laws, we understand things a bit. So let's try to get back to the physical world now, which is the next part of the talk. And I'm not going to try to cover everything. I want to now say we've got lots of one-dimensional systems made out of either atoms or electrons, but it's unlikely that any system is perfectly the Heisenberg model, say, of spins. There's some second neighbor interaction or something like that. Usually there are additional symmetry-allowed terms that may be very weak, but they should be present. And we'd like to make sure, or maybe see how the physics changes once we add those, because even if they're weak, and even if they're irrelevant in the sense that when we go to low energy, they drop out, they still matter if you wait long enough for dynamics. This is not always appreciated, that breaking integrability will eventually show up. Unless you choose a very special initial state, you're almost guaranteed that eventually you will notice that you broke integrability. So the main example that motivated us is one-dimensional metals, which we now call Luttinger liquids. So the Luttinger liquid theory is the realization by people like Haldane that if you take a one-dimensional metal of electrons with interactions, it's actually not like a Fermi liquid. The basic quasi-particles are not the electron. They're more like free bosonic modes. But to say that it's a free theory, the Luttinger liquid action is a free boson, but that's certainly an approximation. We normally throw away some of the other terms because we say they're irrelevant at low energy, but we're going to need to ask, how stable is the free behavior of the Luttinger liquid to putting these realistic perturbations back in? And the answer is we can now see some signs of what was predicted, largely numerically, but then we have a scenario, an experiment that we think would be fun to try. So I'm going to say a little bit about one-dimensional metals in the real world when they're not integrable. I'm going to skip what happens when you put bosons in a trap, which was point 2. I do have some extra slides if anyone asks or is particularly concerned, because that is a natural experiment in atomic physics. And then I'm going to talk about, for the last 10 or 15 minutes, about a few of the things going on with very clean solids above 1 dimension, where extra conservation laws are not so much the story, but you could ask, are there other ways that the electron fluid is different from the standard fluid? And the answer is certainly yes. And some of those are being understood. I certainly can't give an overview of that whole field. So the idea is going to be how does a localized lump of energy spread out in a many-body system is an experiment that we want to propose to see something that we think is not yet, has not really been thought about before in one-dimensional metals. But first, and I'm also going to come back to this in higher dimensions when I talk about a new kind of spin system at the very end. So here's some possibilities for how things might spread out when you create a lump of energy, like in that numerical experiment I just did for the XXE model. If you've got free particles, they fly apart, maybe with different velocities. Fluids, because of nonlinear dynamics, we know can be quite interesting. They might have wave fronts and things like that, but they tend to be ballistic spreading. Diffusion is certainly a possibility. That might be what you'd expect if you're thermalizing. There are exotic cases with disorder and things like that where you could get subdiffusive behavior. You could certainly get localization in something like an MBL system. What I want to talk about is that we think real one-dimensional metals, if you start at low temperature and then heat up part of the metal with a laser, say, which is an experiment that was done in the old days by people like Bob Dines, so I'd like people to try it again. You'll actually see that the energy spreads super diffusively, somewhere between diffusion and ballistic behavior, and I'll say how that comes about. And again, we can check a lot of this with DMRG, and because we know how the integrable case behaves. So this is the same model I was talking about before. Here I want to, for experimental relevance, you could either work with spin chains, or you could work with ordinary metals, which are basically closely related to spin chains. There's the so-called Jordan-Wigner transformation, which means I can exactly rewrite this spin chain on the top line as this interacting spinless fermion model. If I took spin-full fermions, that would be like two spin chains. So models like this are integrable, but I know that if I add extra couplings and things like that, they won't be. So we need a toy model that doesn't have disorder. It's not random. That would lead us to things like MBL maybe, but that doesn't have integrability either. And we're going to study these spinless Luttinger liquids or modified XXZ models. And we know the power of the Luttinger liquid theory is that we know that a lot of things at low temperature are controlled by this free boson picture. It gets the free energy right, for example. We know a lot of other things about the Luttinger liquid. So what I'm presenting is not saying that any of those things are wrong. It's saying that if you ask transport questions and not tunneling, but actually like ordinary DC transport questions, even at quite low temperature, you need to think about perturbations to the standard Luttinger picture. The ballistic behavior that you would get out of solving the free boson is not what actually happens. So anyway, this is testing that we can see that Luttinger liquids do what they're supposed to if you have no integrability breaking perturbation. This is the XXZ model. These are the famous power law correlations, or for students in the audience, one nice prediction that can be seen numerically now is that in a Fermi liquid, there is a jump in the electron occupancy when you cross the Fermi level. Maybe it's 1 to 0 in a free Fermi gas. There's a renormalized jump, but still a non-zero jump. If you have interactions with the Luttinger liquid, you see these cusp-like singularities. Okay, so here's how we're going to break integrability. It's maybe the simplest perturbation we could find that will leave the system metallic, so it's irrelevant, but it is not integrable. And here's how you know that. We're going to add a staggered magnetic field. And this is really work by Christoph Karisch, and it was a heroic amount of effort overall, because the point is basically to find a renormalization group trajectory where all of these points have the same asymptotic long distance correlations. The idea would be that these are all flowing to the same point on the x-axis, which is the Luttinger liquid that we're used to, but that they are not all integrable, only the final point is integrable. The way to tell that is to look at the statistics of energy levels. So H is the strength of the integrability breaking perturbation, and you can see H equal to 0. Level statistics have a so-called Poisson behavior. Basically, energy levels are independent of each other. There's no level repulsion because in an integral model, any two nearby levels are likely to have differ in at least one quantum number which means they don't mix. There's a famous behavior in real models and non-integral models, which is called level repulsion. What level repulsion means is that in perturbation theory, if you remember the energy denominators in second order perturbation theory, you're very unlikely to get two levels sitting right on top of each other. And that's what shows up here. So this is Wigner-Dyson ensemble level repulsion. So this is just proving that this does break the exact solution of the problem. It breaks all those extra conserved quantities. So what does that do to transport? Well, we kind of expect that this should give us a finite conductivity once we've broken integrability. On the other hand, I just told you that it's irrelevant. So how do I reconcile those two? Well, the answer is that if you go to low temperature, the effect of that term does become weaker. The conductivity is always finite, but it blows up like a power law at low temperature. So in this toy model, something that we studied a while ago was verifying the notion, and you can calculate this from the leading irrelevant operator in bosonization, that this is a way to get power laws in transport, that the conductivity blows up at low temperature. It's different from the tunneling power law, but it's kind of similar in spirit. It's because of the way many operators in the Luttinger liquid have a continuously variable scaling dimension. So if you want, this is, now there is a finite conductivity because I broke the integrability, but the conductivity blows up as 1 over the square of the perturbation h, and as 1 over temperature to some non-trivial power, depending on the Luttinger parameter. So now what we wrote up more recently, and just appeared in print about a month ago, is that that leads you to kind of a paradox, or at least an unusual behavior, which is the following. Suppose I think about thermal conductivity to make it simpler, and thermal conductivity is also supposed to have power laws in temperature at low temperature in this kind of model. So that's the first line. So, okay, let me make an equation for how heat should evolve. I should have a heat current over here, some power and temperature, and I should have an energy density. But that leads me to a sort of nonlinear diffusion equation, where if I had kappa going linear in T, I would get ordinary diffusion. That's what happens in metals at low temperature. But if I have any other power, I get a so-called fast diffusion equation. So the point is that even if you tried to make the most boring assumption possible, which is that you have local thermalization and that you can use your linear response conductivity, you're still forced to get something nonlinear when you ask about the expansion of a hotspot in a low temperature background. So can we actually calculate this and see that it's true? Yes, we can see that there is super diffusive behavior, but we can also see that the assumption of local thermalization is a little bit too strong. So in other words, this model makes an assumption that the system is expanding slowly enough that it can sort of reach local equilibrium, but that turns out not to be 100% true. So this is what I've showed you before, that we can do the integral case. This is to get you to believe in DMRG. When we do the DMRG for this integrability broken case, that simple nonlinear diffusion model I wrote down would predict something with more or less a flat top, or at least a monotonic shape. And that's not actually the case. You get something that has this two-peak structure, and you can make a scaling collapse. And so in other words, the simple model of local thermalization correctly predicts that there should be super diffusion, but that assumption that local thermalization is a fast process is not accurate enough to give you the correct shape. And anyway, these are the numerics showing that indeed you see a power law expansion, but it's between diffusion, which would be x going like square root of t, and ballistic, which would be x going like t. So I'd say the conclusion is that when you heat up a Luttinger liquid in the real world, so our generic one-dimensional metal, and the easiest way to do it, the cleanest way for energy would be to work with a spin chain. With a metal, you get into thermal power effects, and if you're away from half filling, it's actually a coupled set of equations that it's a bit more complicated and that is on our list, but we have not convincingly solved yet. The point is that there is a race between thermalization and expansion, and in that race, they interact with each other in an interesting way and give you super diffusion. At least, numerically, you can't go to infinite time. We know that in the simple model, it's there for infinite time, though. So again, these are sort of additional checks that there are these emergent power laws, and we can check that we do get diffusion if the background is at non-zero temperature. So to do this experimentally, you want the background to be as cold as possible, and then heat one spot to a decent amount of temperature and just watch that energy spread out. So there are some future directions even in one dimension, and we're actively working on that. But what I want to wrap up with in my last 10 minutes or so is some of the things going on in higher dimensions, where there are a lot of experiments and there are a lot of interesting things that go on, and they're a little bit different. The reasons for the interesting fluid behavior are a bit different than the ones I just wanted to talk to about. And I'll talk about two examples just in the interest of time. And with both of these, I think the final words are yet to be said. But here's one nice example. So hydrodynamics of electrons is kind of in vogue at the moment because people have more incredibly clean materials. But it should be pointed out, it's actually a field with a pretty long history. I would say theoretically, it goes back to people like Gurdjieff a very long time ago. And then experimentally, two-dimensional electron gases and things like gallium arsenide are very clean. And actually, Lorenz Molenkamp did some very nice hydrodynamical experiments in that system in the 1990s. What's kind of rejuvenated the field experimentally is, first of all, graphene is very nice in a number of ways. It's got controllable carrier density. At small carrier densities, it's basically got a rotationally invariant Fermi surface, and it can also be quite clean. And then Andy McKenzie and other people, Claudia Felser, other groups as well, have managed to make extremely clean crystals. There are some three-dimensional materials that just happen to have very long mean-free paths, and you could hope to see hydrodynamics there as well. And here, a working definition of hydrodynamics, you would like to find materials where instead of instantly having electrons scatter off impurities and lose their momentum that way, the electrons have time to interact with each other many times in a momentum conserving way before they lose their momentum. Because if you remember, a fluid, something like water, it's crucial for water's behavior that there is momentum conservation. We'd like to have a regime in fluids where that applies for a while. And this is some of that old work of Gurdjieff that I mentioned, that basically, I'm sorry that these, a couple of symbols seem not to have translated well in my keynote, but the point is, I've got a mean-free path on which momentum relaxes. That's lambda MFP, or lambda momentum relaxing. I've got a mean-free path for interactions that conserve momentum. And if I can get the momentum relaxing mean-free path to be longer, then I'll get something unusual. While the conventional picture is the one here. I get basically Ohm's law and things like that if momentum relaxation is the most rapid process. If the momentum conserving interactions, like Coulomb collisions without umclap between electrons, if those happen, and in particular, it's useful to think about a physical length scale like the width of a wire. This is equivalent to thinking about like a tube or a pipe that fluid is flowing through. If I can have the wire be wide enough that there is a notion of local collisional equilibrium within the wire, within different spots of the wire, but that I have not lost momentum, then that would be the usual fluid dynamic regime where things like fluid viscosity are important, and things like flowing fluid through a pipe, which is the fluid mechanics version of pushing electrons through a thin wire. People know a lot about that. So the challenge is, first of all, you can take over what people have already done with ordinary fluids. But what I think is maybe more interesting is, how is the electron fluid in higher dimensions different from water or something like that? And there are a number of ways. It could be because of quantum mechanics. It could be because of long-range interactions. And one way is that electrons are charged, which means you can apply a magnetic field and break time reversal symmetry. So here's one of the old Molenkamp papers that I mentioned. And it's known that if you break time reversal symmetry, there is a new kind of viscosity that is not dissipative, and it's known as the Hall viscosity, and it's been studied, and it's been very nice to understand it in topological states with a gap, things like fractional quantum Hall states. That's been quite active. It's also there in metals that break time reversal, and we think it's even been seen experimentally recently. But here's the idea of what the Hall viscosity is and how it's different from ordinary viscosity. Ordinary viscosity means if I've got a shear flow, let's say the fluid on the inside is rotating and the fluid on the outside is not, then normal viscosity is dissipative. It tends to reduce that shear flow and produce heat, say. While on the right-hand side, if I broke time reversal to I need to do that in order to pick out a direction for this other kind of viscosity, then what might happen is that instead of momentum being opposite the shear, it's perpendicular to the shear. And that's just like the Hall conductance that maybe some of you are used to. It doesn't have to dissipate energy because it's perpendicular to the direction of flow. So that's only there once you break time reversal. It's another part of the stress tensor. So what happens to that in a metal? And it turns out that we think it is observed. So one way to look for it is discussed in this paper. What's actually measured, and this gets a bit subtle when you start to think about real crystals, and it's kind of an active topic at the moment. But if you're thinking about a simplified translation and variant picture, then it's fine. What you're normally measuring is effectively how conductivity is modified when you change length scale. So here, Q is some wave vector, and it's known that the order Q squared corrections to sigma xy are a good way to probe Hall viscosity. But if you want to be very precise, what's actually measured is not directly the viscosity, at least in the experiments I know about. It's actually the Q squared component of sigma xy. That is, it's like the finite wave vector correction to the Hall conductivity. So you can calculate that. It turns out that the key technical result that went into our calculation is by Alexeyev, and it's basically how do the components of the viscosity tensor depend on this mean free path and on the cyclotron orbit. You need a model for boundary conditions in the channel, and you can get a prediction, which is that basically for realistic circumstances, you can see that the channel will modify the Hall resistivity because of the viscosity of order 25%, which we think might be measurable. It turns out that it may not be measured in Andy Mackenzie's experiments, which is what originally motivated this, because his material is actually too ballistic. It goes from being diffusive at high temperature to being almost free at low temperature because the Fermi surface is big, and because basically Landau was right that Fermi liquids are very stable. If you have a large Fermi surface, there's not that much scattering you can do because of the Pauli exclusion principle. That's why graphene may actually be better. And indeed, there is a claim by Andre Geim's group that they've seen the Hall viscosity in graphene using a slightly different method. So the last thing I wanted to finish up with is a new system. And I only have 2 slides, but I was just hoping to advertise it and get people excited. And I think there is a talk by Norman Yao that might be online with a whole lot more details. So this is a big team. It's experiments in Norm's group. Chris Lauman and I were involved in some theoretical analysis. And the basic idea is that it's a way to capture exceptions to hydrodynamics for 2 other reasons. One is disorder and one is long-range interactions. But let me say what's going on in the system and then why this seems to throw up some interesting questions for people to think about. So the idea is this is a spin system of isolated defects in diamond. Basically, there are 2 flavors of defects that they can address. And what they are doing is driving a local spin polarization and then watching how that evolves in time. So we're going to make an idealization in our theoretical analysis of this, but it seems to be testable against the experiment. And that is because these are defects that sit in random locations and also have some randomness in their local fields, it seems like then rather than thinking about something like a Heisenberg model on a uniform lattice where things might move ballistically and quantum mechanically and so on, it seems that the right way to think about the dynamics in this system is that basically you've got pairs of spins that interact. You've got some rate of hopping from one spin to the other. So you've basically got like a classical rate equation model. And you might say, well, what could be interesting in classical rate equations as far as hydrodynamics? Shouldn't you just get diffusion? And it turns out that there are some modifications to diffusion. There are at least 2. One is due to disorder, and the one that's connected to something I mentioned already is that it turns out this is a case where long-range interactions are there and make a difference, but it's not such a big difference that it spoils things like convergence of thermodynamics and reaching some form of equilibrium and so on. So this is all about the fact that the dipole-dipole interaction between spins, well, that's 1 over r cubed as a term in the Hamiltonian. If I assume this kind of incoherent hopping I talked about and convert it to a rate, it's like a hopping rate of 1 over r to the 6th. And 1 over r to the 6th is kind of magical in 3 dimensions. I don't think that's why Norm was working on this system, but it has a nice feature, which is it's in this intermediate range where basically, if you had short-range interactions or long-range interactions that fell off more rapidly, like r to the 8th or something, you essentially get normal diffusion. The long-range interaction is sort of irrelevant. If you have ultra-long-range interactions, like if you had a plasma or something like that, then you can get Levy flights, more complicated things. But there's an intermediate range where these long-range interactions are just enough to modify the way that you reach equilibrium, but the equilibrium you reach is still the same one. It's still a diffusively spreading blob. So we think that's part of the story for this experiment. There's an equally interesting part, which is about the disorder in the system, but that's a little bit farther afield from what I've been talking about here because I've been trying to ignore disorder. So I've just used disorder because it's necessary to justify this kind of incoherent hopping model. So I promised I would wrap up at 50 minutes, and we're at 51, so now's a good time. And let me try to summarize, since there were a fair amount of different things in this talk, what are intended to be maybe the general conclusions or lessons. So hydrodynamics, broadly speaking, is, you could say, some classical emergent description, and we're interested in it for underlying quantum models. You could say everything in nature is an underlying quantum model. Fine. We start with some quantum equation, we get some classical equation as the long-time description. But the ways that can be modified, well, the way that's now very well established is that the extra conservation laws in 1D give you a modification of hydrodynamics, which is like a Boltzmann equation for particles that delay each other but don't really scatter each other. And that works very well. When you try to get back to the real world by adding integrability breaking perturbations, integrability breaking is always dangerous, I think, except for fine-tuned initial states and things like that. The long-time behavior is modified by breaking integrability. However, you don't immediately just collapse into ordinary diffusion and things like that. In Luttinger liquids, in what we think is maybe the most important physical example, you actually get kind of a balance that leads you to nonlinear diffusion of energy. And you could do the same thing with charge if you wanted. But basically, the irrelevant perturbations in a Luttinger liquid mean that at low temperature, thermalization is very slow. And that if you have the right dynamical problem, like how things move around, thermalization is not quite rapid enough to give you standard diffusion. So we would love for someone to either re-examine old, or basically to redo old experiments a little bit more carefully to look for signatures like that. And then some things in this problem that are emerging. When you go to higher dimensions, I think extra conserved quantities are probably not the key to the story. What does seem important is that you have electrons in a solid that might have lower symmetry than a conventional fluid. The example I talked about was breaking time reversal. But you could also ask, how is a fluid different because the background breaks inversion symmetry or some other crystalline type symmetry? And now that we have these ultra clean materials, I think that's an exciting area. And then the spin ensemble case I talked about is another kind of dynamical process. And there, that seems to be a case where you actually can say something about long-range interactions that at least eventually experimentally one hopes could show up, that it is relevant in that case that the spin-spin interaction is not just Heisenberg, it actually has this long-range tail, and that's the dominant dynamical effect, we're pretty sure, at the longest times. So with that, it may have been tough to stay silent if I said anything objectionable, but I think I will hand over to Phil to take questions.
All right, yeah, great talk. What we're going to do is you can either submit your question in the Zoom chat, just make sure you chat to everybody, and I can read it, or Joel can actually read it in the chat himself. Otherwise, you can raise your hand using the raise hand button, and I will unmute you and you can talk. Okay, so Greg, you have a question, and yeah. You're unmuted. Okay.
Yeah, I did it myself. Hi, Joel. Good to see you. Very nice talk. I have a basic question about probing this hydrodynamic regime experimentally. Do I understand correctly that you have to address the question of which regime you're in by looking at some process of relaxation towards equilibrium? Or is there any equilibrium probe of whether you're in a hydrodynamic regime?
That's an interesting question. So for some cases, there is an equilibrium probe in the sense you would realize okay, at least if you had the thermodynamics, so so we could ask what information is available if you're not perturbing at all from equilibrium. If you have linear response, then you could tell that the conductivity is infinite, for example, because of conservation laws. If you have thermodynamics, I guess you could probably ask about, does the thermodynamics look like it's got a Gibbs ensemble with one conserved quantity or more conserved quantities? But I think the only simple answer I can give is I think at equilibrium it would be hard. I think if you can do linear response, then the relaxation of a current gives you a measure of this momentum relaxation time. So that's why you want systems with high conductivity in general, because that usually means the current relaxation time was very long.
Mm-hmm.
But you don't want them to just be ballistic. So I think what's harder to measure, I think it's probably pretty easy to measure near equilibrium the current relaxation time. What's a little bit harder to measure without a detailed model, I think, is the momentum, is the fact that there are momentum conserving interactions happening. So for example, what was a little bit tough, I think, in the Mackenzie experiments was to distinguish ballistic behavior from hydrodynamical behavior. I think you can tell either of those apart from ohmic behavior, but to distinguish between ballistic and hydrodynamic, I think needs, at least at the moment in the examples I'm aware of, that needs a bit of modeling. Then I mean, this is a neat thing about Fermi liquids. What happens is if you're at low temperature compared to E Fermi, you kind of start to turn off the momentum conserving scattering because there's very little phase space for two electrons to bounce off each other and go into. So what seems to happen is that metals with high density of electrons and therefore large Fermi surfaces actually wind up being too ballistic to show hydrodynamics at low temperature sometimes. So what people are maybe now looking for mostly are things like semiconductors or things like graphene, where the carrier density is fairly low. It seems like that is more likely to give you interactions that are strong enough to see interesting stuff rather than, I mean, ballistic behavior is very interesting stuff, and that was a big topic of mesoscopic physics some time ago. But for the what we kind of want now is strong interactions, but very clean. And that seems easier at low carrier density.
Okay, so I have one follow-up question to that. So, I mean, there's been a lot of work, yours and others, on understanding and trying to achieve this hydrodynamic regime. But I guess another point that's not clear to me is, suppose we have the hydrodynamic regime, is there kind of like an interesting consequence in terms of like, instability to some kind of order or something like that? Or, why do we want to find hydrodynamic regimes? In other words,
yeah. So I think the last thing you said is something I agree with. Regimes. I think there is more than one different kind of hydrodynamics, and what's interesting to me is that there might be not just one universal hydrodynamics, but that we'll get different things that you can't see with water. So I don't know about an instability as far as an equilibrium phase, but there are instabilities in terms of vortices, turbulence, things like that. So right now, for example, the electron fluid, I think in both graphene and in Andy Mackenzie's cobalt dates, is fairly viscous. On the length scales and currents that they're measuring, the Reynolds number is about 0.1 to 0.01. So that means you get kind of viscous stable flows. If you could, increase the velocity or change other aspects to get the Reynolds number to be larger than 1, then I don't know if you would count, it's not an instability in the sense of an equilibrium phase diagram, but you would find that if you tried to make a uniform flow, it would break up into eddies and vortices and things like that. So that would be just an instability of classical fluid flows. I mean, to me, what I think is neat about being in crystals is just that if you open up a book on fluid mechanics, practically the first thing is we're going to assume isotropic medium, and we're going to assume time reversal symmetry. Neither one of those is a very good assumption in a crystal. So then it comes into, if you have like a magnetic material, suppose you have an antiferromagnet, then the way that the magnetic material influences the electrons is not so much through a B field, but it's through Berry curvature and things like that. So now you have, how is fluid mechanics modified when your particles are moving in a medium that sort of intrinsically causes them to curve because of Berry curvature? So questions like that are interesting to me. I mean, I can't say, I think it could lead you to new, potentially useful transport behavior. I don't know that it's going to say much about thermal equilibrium, but as an example, with fluids, you cool your computer, at least for many, I don't know if this is still true, but in the old days, in laptops, there was always a so-called heat pipe that actually used water and the fluid mechanics of water to keep the machine cool. So suppose you could do that with electrons, that would be nice in a way. You could probably make it smaller because basically taking advantage of some of the nonlinear aspects of fluid motion in water. So I could at least imagine useful transport phenomena, which might include instabilities like turbulence, say. I don't know about equilibrium instabilities.
Okay, great, thanks.
Okay, so Yang-Zi, I saw you raise your hand first, so I'm going to unmute you now.
Hi, Joe. Thank you for your nice talk. Can you comment on one-dimensional system with multiple channels? Because we know that 1D is special because the momentum conservation, energy conservation are basically very tight related to each other. But if you have multiple channels, in principle, the equilibrium process will be quite different. So I'm just curious about this.
Yeah, I mean, the only thing I've actively tried to do with multiple channels, it ought to be possible to cross over from 1D to 2D by having, say, multiple channels with different currents flowing in them and seeing the emergence of viscosities. And I did work a tiny bit, although it wound up being more specifically about energy drag between wires with student Wilbur Denyer on that. So I guess I think it is an example. Okay, so the main interest I had in multiple channels, I think if you have counterflows in the different channels, you could view that as like some kind of quantum limit of viscosity or of two-dimensional problems. Regarding your question about how multiple channels might modify relaxation times and things like that, I haven't thought about any general rule for how multiple channels would modify. I mean, I imagine you would get different exponents. I mean, I think you could get it, it would be different in the details, but I think you could still find, I mean, as long as you could still find irrelevant integrability breaking perturbations, I think most of the story would be similar. What may be true is I think there are fewer of those perturbations and you're more likely to do other things when you add perturbations with multiple channels. But to me, multiple channels are interesting because it's kind of the quantum limit of a fluid, so of a 2D fluid. So that would be neat to look at.
Thank you.
Of course, I'm muted. So next person we'll have is Yigal. I'm going to unmute you. Yigal.
Yeah, thank you. I have a short question for John. Thank you for the talk. You mentioned topology in passing at some point. Do you expect different behavior when you are, for example, at the edge of nu equal 1 quantum Hall system interacting one compared to the fractional quantum Hall one?
I guess there's the theoretical answer of what I expect, and then there's what's actually seen in experiments on quantum Hall edges, which I don't completely understand. I guess in the chiral Luttinger liquid, I think that so that's saying if I have most quantum Hall states, I have some idea of their edge in the Luttinger liquid picture, and I could ask, what are the perturbations to that would be allowed, and could they do things like this? I think a chiral Luttinger liquid, if all the modes are moving in the same direction, I think it would behave very differently. There's kind of a limit to what perturbations can do. I would think if I had a Luttinger liquid, I mean, I think Haldane called this topological instability. I would think that there are perturbations in a Luttinger liquid with counterpropagating modes. Sometimes there are perturbations that effectively annihilate a counterpropagating pair of modes. And that analysis would be a lot like the non-chiral Luttinger liquid we dealt with here. And then there's the intermediate case. So I guess I'm saying chiral, I don't think the effects that I talked about would matter. Non-chiral in the sense of allowing a pair of modes to cancel, I think would be very similar to what I talked about. And then the case like 2/3 or something where they are non-chiral but can't cancel, then I really don't know. But I guess, I mean, I would think that at linear response, it may be that we know the examples like Kane, Fisher, Polchinski of the instabilities that can happen there. I mean, the real world of experiments, even on the integer edges, experiments like Modi-Heiblums and so on, I don't think I understand. I'm not sure that there's a universally accepted explanation even for some of the integer edges in his experiments. So I don't know at this point the full status of the chiral Luttinger liquid theory once you get to realistic transport experiments. So all I can say is theoretically what I would expect to happen in that theory. I mean, I guess what what seems to be going on in experiments, at least one way to look at some of the effects is that they're kind of effects between quasi-particles, bunching and things like that, that are stronger than one might have expected them to be irrelevant based on the chiral Luttinger liquid theory. But they seem to have effects on experiment in shot noise and things like that. But I've just seen talks. I don't know that I have a professional opinion on what terms are required to create that and how those would modify Hydra.
Okay, thanks.
Sergio, sorry. Got oh.
Can you hear me? Yeah.
Yes.
So I know I was saying thank you for a nice talk, Joe. I actually was wondering whether you comment this issue of the fact that when you do experiments, of course, you will be doing them at a finite temperature, and there will be dynamical effects of the lattice. Just so how is there a limit on how strong that say if you're looking at electrons in a lattice, so how strong that interaction would be, or
well, yeah, that interaction is really okay. So if I'm at room temperature or something, it's very hard to see hydrodynamical phenomena because the electrons bounce off of phonons, and that is a momentum relaxation time. So what can happen in some cases at very low temperature is an interesting combined hydrodynamics of the electrons and phonons, things like phonon drag thermopower. So that's saying if you had a very clean material, low energy phonons tend to be very ballistic, even more so than electrons, because a low energy phonon has a hard time scattering effectively. So you could imagine a sort of joint hydrodynamics of the electrons and the phonons. I don't know any really good papers on that aside from these kind of phonon drag thermopower where you have electrons and phonons reaching a moving equilibrium. So that's the one example I know where the phonons are doing something other than just providing a momentum sink. But definitely the standard answer would be you want to keep the phonons as far away from the electrons as possible, and that's one reason to go to low temperature.
Right. But I mean, it might be like in graphene, presumably the coupling would be weak, the electron-phonon coupling would be weak, as opposed to, say, in the Mollenkamp experiments where it was a polar material.
Yeah, I think that is yet another advantage of graphene.
Right.
But I mean, I guess, yeah, it depends a lot on, I think, you know, in the gallium arsenide system, you do have some control of doping and things like that. Maybe it's possible to minimize it, but probably it will never be as good as graphene.
All right, thank you.
All right. Oh, sorry, I lowered. Good. Well, okay. Masood, you can raise your hand again so I can unmute you.
I unmuted myself. Is that okay?
Yes, I can hear you.
Yes, good.
Hi, thanks, Joel, for the nice talk. You showed some results for an XXZ with integrability breaking, I think with the, right? So, and then did I understand correctly that the zero frequency conductivity was diverging with temperature at zero temperature? Is that...
That's right. If you go down to lowest temperature, so basically it diverges as h to the -2 times t to the minus some variable power, okay, depending on the Luttinger.
So did you? I think you said something about this reflecting the fact that it's an irrelevant perturbation. Does that mean that if it's a relevant perturbation, you expect it not to diverge but to saturate at zero temperatures?
That's right. And the simplest thing a relevant perturbation can do is open up a gap. And if you open up a gap, then I would think the conductivity will become very small at low temperature. So what case that I haven't considered, so I guess the two cases I feel like we know what goes on is if it's irrelevant, then you stay in the Luttinger liquid. If it's relevant and gap opening, then the conductivity is small. If it were relevant, but did not open a gap, then it's taking you to some kind of gapless 1D state that is not a Luttinger liquid. And then I don't really know what happens.
Yep.
Could be interesting.
Thanks.
Okay, and we have one one question from the audio or from the chat by Anosira. I think that's how you pronounce it. And the question is, what about instabilities induced by interactions with the lattice, excitations, aka like phonons or Peierls distortions? Would they destroy the thermodynamic regime? And I think you kind of addressed this, but maybe you can specify this.
Yeah, I guess there are certainly equilibrium instabilities. You know, you could open up a gap through something like Peierls mechanism, and that would take you out of hydrodynamical regime and give you an insulator. I mean, I think there are cases. What I don't know is if you're right on the verge of an instability where you have kind of a diverging lattice response. Like, I mean, I think a case that would be interesting would be if you were right at like the paraelectric to ferroelectric transition or something, then you would expect the soft modes of that transition to be an additional degree of freedom. And maybe those can be underdamped at low enough energy. So I guess that the standard answer would be that phonons will make a difference by carrying momentum away from the electrons, so setting an upper time limit. And they will also make a difference if they just give you a new phase, like through distorting the lattice. You could be on the boundary of a phase, and maybe then you'd get an actual modification of the hydro.
Okay. So is everyone all set with questions? Then I think we can wrap this up. Thank you very much, Joel, for your wonderful talk. And I don't think there are any announcements. I think next week we'll have a talk at the normal time, but otherwise we will send an email out with a reminder ahead of time. All right. Thank you very much, everybody, and see you all later.
Great. Thanks, everyone. Hope to see you in person sometime before too long.
All right. Bye-bye.